I would now like to introduce our speaker. Miguel Villarreal is a research geographer with the USGS Western Geographic Science Center in Menlo Park, California. But I hear he's dialed in today from Tucson, Arizona. Welcome, Miguel.
Hi, thank you, Mary. Can you hear me all right?
Yeah, sounds great.
Okay, great. Okay, hi everyone. Thanks for dialing in today, and I'm going to talk a little bit about our research on the Colorado Plateau, developing remote sensing time series to look at post-abandonment of oil and gas pads. Okay, so I just wanted to put a few faces to the names with my co-authors here. So this is me, Miguel, and I'm from Menlo Park, the Western Geographic Science Center. And my team in Menlo Park who have done a lot of this research that I'm going to talk about today are Eric Waller, who's a postdoc down here, and Travis Poitras, who's a student contractor with the Western Geographic Science Center. And our collaborators in Moab, Utah, from the Southwest Biological Science Center of the USGS. For this part of the project includes Mike Duniway, a research ecologist, and Travis Nauman, USGS postdoc. And they gave a webinar I think about a year ago on some of our initial results of these projects. So I'll touch on that a little bit as a refresher and then move on to some more recent accomplishments. So some background on the larger USGS project. It's called the Southwest Energy Development and Drought Flood Project. And I think this is about our third year. And it's a multi-center USGS project, so it includes SBSC, Southwest Biological Science Center, us over in the Western Geographic Science Center, the Western Ecological Research Center, and Fort Collins. So we've got a different group, and we're all working on different aspects of the issue, starting to look, this first part of the project, on the impacts of oil and gas development on ecosystems in the Colorado Plateau. So we've got a lot of questions we're trying to address here, how energy exploration and development may influence things like recreation, economics, ecosystem services. We're looking at things like dust and habitat loss, fragmentation, influences of energy exploration and development on air quality, and so on and so forth. So we've got some big questions we're looking at. This first part of the project is focused on restoration activities. So we're trying to look at how these pads, after they've been abandoned, how the restoration and reclamation activities are going, and what we can glean from the past, and how we can help land managers and industry folks better improve upon these restoration activities. A little bit of background on the issue. So the trends in oil and gas development have increased pretty steadily over the last couple of decades. This is just information for Utah, the number of wells per year, starting in the 1960s, and we see a pretty large jump here up into 2010. A slight decrease in recent years due to the lower cost of global energy, but we expect to see in future years, increased focus in this area on extracting oil and gas. So this is a major issue, and it has a large footprint across the region in the form of roads to get into these areas for exploration. And then the pads themselves, while usually pretty small, in aggregate, they have a large footprint and can have some major effects on dust and habitat fragmentation and these other issues that we're studying. So I'd like to start out some of these presentations with some aerial imagery showing the footprint of these oil and gas pads that we're talking about. So these are a series of aerial photographs. This one's starting back in 1997. This is near Vernal, Utah, black and white. So you can see some of the roads in this area, but not much development. If we move ahead into the future to about 2004, we can start to see the footprint increasing, and then things really start to pick up. This is 2008, and we can see proliferation of roads and pads, and some of the different activities going on these pads. by 2009, it's really, the footprint has maxed out in this area. 2015, it's staying about the same, so not much more development. And the size of the pad starts to decrease a little bit due to some of the reclamation efforts at that point in time. So once these pads are, once the exploration is done and they move to the pads and start to produce vegetation, soil are removed for drilling and other operations. Once they're abandoned, so depending on the lifetime of the pad, there's some intervention, different levels of intervention, depending on the land ownership and management and the time when it was abandoned. But the soils and vegetation are usually topsoil is usually put back on and some sort of vegetation planted in an attempt to restore this back to some sort of habitable system. So we're trying to use our remote sensing to assess how these things have changed over time in terms of vegetation cover and reclamation success over large areas. So we can look at multiple paths over the entire plateau and help land managers and industry with future implementation. So the general objectives of reclamation, this is from the BLM Gold Book from 2007. The long-term objective is to fully restore the ecosystem, including natural vegetation, the hydrology, and wildlife habitats. But in the short term, the operator's generally interested in restoring some sort of stability to the site, the visual, hydrological, and vegetation. And they're responsible for the sort of initial attempts at this, and the land management agency, BLM or whoever, is responsible for helping get it to the final level of complete restoration down the line. Here's a photo of this is going to be of a single well showing sort of the lifespan as the footprint through production and reclamation activities. So this looks like a sort of a pinyon juniper system out here. You see the road come in, pad. At this point in 2004, it's probably productive at this point. By 2006 here, the footprint is starting to shrink. Maybe some topsoil has been moved back in, some vegetation planted, and likely at this point, it looks like it might have been abandoned. And by 2009, it's completely abandoned, and you can see that there's been some planting here, like some herbaceous vegetation and some vegetation along the road as well, closing that off to access. And 2011, you can see the increase in vegetation cover. And then the end point of these photo series, this is 2015, you can see this area has cover, so there's less bare ground, less possible soil erosion at this point in time, but not fully restored to what the surrounding vegetation looks like, in this case, pinyon juniper. So we're trying to assess these changes over time to see how closely using remote sensing they can get to surrounding vegetation. So there are three points I want to talk about today involved with this research. And the first thing we did is looked using some field data from the Colorado Plateau around Canyonlands National Park. We wanted to identify the best spectral information we can get from Landsat imagery to monitor changes in vegetation and bare ground. So I'll talk briefly about those remote sensing specifics. We found some pretty interesting results there. Then we take that information and we move on to developing time series from Landsat archival data from 1984 to about 2011. We developed time series of almost monthly intervals, and we do this in Google Earth Engine, cloud computing, and then we use statistical software to develop statistical models of changes in that time series related to development and post-abandonment recovery. So I'll talk about that process. And then we looked at the series of abandoned wells across the plateau and looked at how they had recovered or how vegetation has changed at those sites. And then using temporal and spatial environmental variable, we try to look at what may influence the differences we're seeing in the vegetation cover at those sites. So we sort of have the hypothesis that it might be climate or precipitation during the time of abandonment that would influence how well a site, how the vegetation recovers on that site. So we look at a bunch of variables and create models, and I'll talk about those results as well. So the first part here is focused specifically on the remote sensing. We have a paper in review right now on this this part of the research. It's called Identifying Optimal Remotely Sensed Variables for Ecosystem Monitoring in Colorado Plateau Drylands. And what we did for this is to get a better handle on what sort of spectral information we can use across the plateau for our modeling for this SWED project. We wanted to have something that was based on field information, and in this case, the best stuff we had was located around Canyonlands National Park and the Indian Creek grazing allotment, BLM land of the Dugout Ranch, and there were a series of monitoring plots established there in 2006, 2007, 2008, so 315 plots, a large number, and they were resampled in 2004. So these are basic line intercept plots, about 50 by 50 meters, with information about cover of vegetation and soils and biocrust, native and non-native vegetation. So we use these. They're a little bit larger than a Landsat pixel, which is 30 meters, but pretty good information and pretty well distributed across vegetation types for us to get a good idea of how to model these with imagery. So we use this Google Earth Engine cloud computing, which is great. It's all online. It's really fast. Google Earth Engine takes in a lot of the NASA and USGS imagery, Landsat and MODIS and all those things, and it's hosted on their servers. And you can call it up and process it really quickly using their cloud computing platform. So a pretty vast improvement on the time it takes to do some of these things. So in Earth Engine, we could calculate a bunch of different spectral indices from Landsat data. And for this study, we did 12 different indices, kind of interested to see what would capture variability in these different vegetation types. And we focused on separating them into groups that account for green vegetation, like NDVI is a pretty popular one. And then things that, indices that capture non-photosynthetic vegetation, since there's a lot of that on the Colorado Plateau. And then soil as well, for percent bare ground. So based on this plot information, we developed for these 5 different vegetation communities that span sort of the elevation gradient, going from grasslands at the bottom, sagebrush, blackbrush, blackbrush juniper transition area, up to pinyon juniper sites. For each of those communities, we developed percent cover models. So total live vegetation, bare ground, percent cover of biological soil crust, exotic native vegetation, perennial vegetation, and tree cover. So we created a specific model for each one. And this is sort of, this is the breakdown of our indices here. I won't get into too much detail on these, but the green would be the photosynthetic vegetation group, so NDVI and cap greenness, and then we had a couple that were specific to NPV, soil adjusted total vegetation index. This index, we made the non-photosynthetic vegetation normalized different index, and some that were more sensitive to soil brightness. So using all these indices, we tried to create for each of these cover types within the different vegetation communities, just a simple linear regression to see if one index would do a good job of capturing all that variability. And then multiple regression models where we just kind of threw them all in there to see which one would, which different indices or spectral variables would explain most of that variance. And don't worry about this table here. The important thing that we found is that for all these vegetation types that we're looking at, the percent cover of bare ground could be really accurately modeled with a single index And this is typically one that was based on a combination of the red band of Landsat and then the shortwave infrared bands. And so for all these, the bare ground category for the different vegetation communities, we're getting decent R-squared and RMSE errors. And we did pretty well with total vegetation, but bare ground and percent bare ground cover was pretty accurately modeled. Here's an example of what that would look like. This is a SAT-V index that we're using, going from 0 to 0.12 and percent bare ground on this axis. So as your bare ground decreases, your SAT-V is increasing. So we've got a pretty good relationship here in the grasslands, and this is sagebrush, R-squared of 0.35, which is actually pretty decent for this type of remote sensing imagery, especially when it's based on point intercept plots, 50-meter field data. And this is the black brush, percent bare ground versus SAT-V. So the soil adjusted vegetation index turned out to be one of the best models in almost all these systems to get at bare ground. So we figured, okay, using this, we can look at these changes over time in bare ground after the abandonment of these oil and gas pads. If you're interested, and this is a point for folks who are doing work in Colorado Plateau and these other dryland areas, that we would highly suggest looking into the SAT-V as an index to monitor vegetation cover changes because of these band combinations. It looks slightly complex, but it's not too bad. And just to give you an idea of how this works in the remote sensing world here, this is the reflectance that you get. These are the wavelengths in the electromagnetic spectrum here. So from smaller wavelengths out into the short wave, and then you get out to the thermal. But these are the different spectral profiles of vegetation cover in green, and NPV or non-photosynthetic vegetation in orange here, and then soil in the brown color. So you can see some differences in the way the reflectance is between these. And so what the SAT-V does is it uses this red band here, band 3 in the equation, and then the shortwave 1 band. And you can see major differences between vegetation and NPV and soil in that shortwave band. So it's really good at capturing the soil NPV aspects of reflectance in these plots. So it's just a ratio of those two bands, the shortwave and the red, and then there's some soil correction stuff, which helps reduce the influence of bright soils on the reflection. So it uses a standout here, band 7 shortwave, which separates out soils from the non-photosynthetic vegetation. There's a difference there, and so it uses that to sort of punish areas that have bright soil reflectance that may be influencing the sea. So it's pretty easy to calculate like an NDVI, and it turned out to be pretty robust in this case. Okay, so that's it with the beacon out on the Landsat there. I'm going to get into now developing the time series of fractional plant cover using SAT-V on abandoned energy development sites. So the study region here, Colorado Plateau, we got all the information we could on oil and gas pads in the region, active ones, abandoned ones. Some of them go back to the 1900s in the records. So state of Utah, state of Colorado, and New Mexico all have pretty reasonable geodatabases with this information. So we collected them from the states and aggregated them together. And the initial amount of points we had, or gas pads, was about 90,000, and we had to get this down to something reasonable based on what we wanted to measure. A lot of these records, to start with, had inconsistent data, what was in the attribute tables, but at the very least, they tended to have information on when it was originally drilled, date of abandonment, which is important for us, and then usually who was responsible for the well and ownership. But we found pretty quickly that there are a lot of errors in these attributes in terms of when they say they were abandoned and drilled, and also spatial errors. So there'd be points, 50, 100 meters away from what we could see as visually as a well pad. So we spent a lot of time validating and looking at Google Earth high-resolution imagery to make sure everything was what they said it was. So to get them down for this study to a reasonable number, we had to filter them by year and status and land cover type. So we just kept the locations that were plugged and abandoned. We're not interested at this point in sites that are still active, because we're looking at recovery over time. And then we just looked at wells that were plugged and abandoned between 1997 and 2005. So using aerial photography, we could sort of assess during that period whether or not these were truly disturbed sites. And then we would move the points to where they needed to be to make sure that we were sampling the correct pixels, and then made sure that they were got rid of all duplicates and ones that were still active or had been sort of re-drilled later in time. So we ended up with about 1,866 at this point, and we further refined them because we wanted to fit within this Landsat time period between 1984 and 2011. So we chose ones that were just drilled after 1984, which would give us at least a year of time of Landsat data to see what it was like before it was cleared. And then if they had to be abandoned between 1997 and 2005, which would give us at least a 5 or 6 year window after abandonment to see how the vegetation is recovered at that site. So for these 510 sites, in Earth Engine, we can calculate a time series, which is, it varies a little bit, but you know, it's a 16-day return for Landsat, depending on clouds and all of a lot of different factors there. You could have one value per month for each of these sites, SATB value. So we calculated for each of these wells a complete time series. And then we did that as well for some reference pixels that we used to compare them to over time. These are the DART pixels, which I'll explain real briefly what those are. And Travis and Mike did a webinar on this last year, as I mentioned. This is the Disturbance Automated Reference Toolset, and there's a paper out in Science of the Total Environment. It was published this year, if you want to take a closer look at that. But what this does is combines a lot of environmental covariates across the region, soils, topography, geology, combines them and then looks at the site of, say, a well pad or some pixel, and then finds sites that have similar environmental conditions around within a 5-kilometer area or so of that site that would have similar conditions. So we consider that to be a reference. It would have the same sort of environmental potential for vegetation and soils, et cetera. So using this DART tool set, we can compare, in this example, this well pad with these grayed out areas here would be the reference pixels. So we can have a lot of different values of satellite pixels within there to compare and look at how that pad is doing either in a snapshot. And in this example, this pad would have a pixel value down in the lower, brighter part of this these SATB values, and the other reference pixels, this is a distribution of those pixels. And so we can look at that over time and see how that pad is sort of increasing or decreasing in cover relative to its undisturbed reference pixels. And this is sort of how it looks on the ground. If we go out now and look at SATB values, say from this one that's plugged in 2010, and look at its reference site, this one would have a SATB quantile of 0.14, so it hasn't really recovered very close to its surrounding reference pixels. Here's an example of one that was plugged and abandoned in 1976, and its reference site, and this is much closer, not quite there, but closer to what the reference sites are. So this just gives us a way to evaluate that pad relative to other areas. And in terms of a time series, it's great because, you know, with the vegetation cover changes due to phenology and greening up during different time periods, this really standardizes that time series and gives us some sort of confidence in what we're seeing is not just, you know, regular fluctuation of herbaceous vegetation. Okay, so this is what our time series looks like. On our x-axis, we have time from 1984 to 2011. This would be our SATB values plotted as a percentile of the DART reference pixels. And here we would have our sort of pre-disturbance time series. And just to show you some more photography here, this is what it looks like. This is the same well in 1997, about this time. The reference pixels are likely these surrounding areas. It drops down, all these time series drop down pretty rapidly once they are cleared, and that's a pretty obvious thing to map. At this point in 2004, around here, you can see that it's much lower than the reference pixels at that case, and it's during the active phase. By 2006 or so, it has been no longer active, but it doesn't look like much reclamation's been done, so we're still sort of in this trough of disturbed period. But then we moved to 2009. You can see there's been some effort to revegetate the area, and our SATB value is getting closer to those reference pixels and back to its sort of pre-disturbance point in time. And 2010, in this particular case, the area is actually pretty well vegetated, and we're about here in the time series. So we ran these time series for all the wells, the 510. And one more thing I should point out here, which is pretty interesting. In some of these time series, you can see changes within the production phase of the shrinking of the well pad size. So initial disturbance is usually pretty big, and we're getting this big drop here. But then as production ensues, a lot of these areas are temporarily restored, these gray areas here, and you can see that the SATB starts to creep up in those pixels that we're monitoring. And then usually once production's done, we have a pretty steep drop. A lot of these sites are cleared again, completely cleared, and then the topsoil is put back on and they're reseeded at that point, so we get another drop. And then into our post-plugged and abandoned phase. Okay, so we take the time series and we develop a model of a model fit for each of these time series. So this is similar to one that we've seen before. This is a program that we use in R called BFAST, and it will basically fit trends to your time series. So we use these to identify big breaks and estimate our changes in vegetation. So this is our pre-drilling phase. This would be our approximate drill date, approximate plugged and abandonment date here, and then this whole period here we consider sort of the recovery, revegetation phase. So our model that we create to estimate what that value is with the Landsat, I'll just walk you through this really quick. We'll call it the relative fractional vegetation cover, which is just how much vegetation is at the stem point relative to the pre-drilling vegetation. So simple fraction based on this A value, which is the lowest point when it was plugged and abandoned, and 5 years, we're using a 5-year window here after it was abandoned for that value. In this case, we have a value of about 30. And then we look at that relative to this drop here from the pre-drilling median, so where it was before it was disturbed. See that low point right when it was drilled, which is our B here, and that example is about a value of 50. So using that, we'll calculate this RFVC, which is about 0.6, and so that would be about 60% recovery to our revegetation to its pre-drilling median. And then we could estimate a recovery or revegetation rate based on that 5-year period, which is about 12% per year after abandonment. So those are the metrics we're using to look at how these have changed across the region. I see some questions coming in, and I wonder if I should address those now or if I should wait till the end. Just let me know. So one of our hypotheses with the time series, which makes it interesting, is that we can look at when These sites were abandoned, and when they were assessed and asked questions about the climate and the precipitation during those exact periods and see if that has any influence on the way different sites are recovering and the patterns across the region. So this is a graph of something called the Standardized Precipitation Evapotranspiration Index, which is has a 6-month window, which is incorporating precipitation, mainly precipitation information. This would be over a time period of 1997 to 2011. You can see this would be a sort of a wetter period, and then getting into sort of a drought time, and different years have higher SPEI than others. So we wanted to look at those as a potential influence on recovery. So we're interested in looking at a site example here in 1997. It was abandoned in 1997. Does this really wet period influence how that site revegetated? Or if we're assessing it 5 years later during a drought period, would that have more influence on how the site revegetated in those RVFC scores? So this is kind of the question we have. We see a lot of variability here, and a lot of differences between when they were plugged and abandoned and when we're evaluating them. So I'll talk about how that plays out in just a moment. So we did a little data mining. We have our RVFC fractional vegetation cover values for each of these sites and all these different years. So we ran those through a random forest statistical model with a bunch of environmental variables to see if any of these things popped out as influential on these values that we're seeing. So we threw in things like we have a bunch of soil variables, regap vegetation classes, so our different vegetation communities more responsive to reclamation. We developed some specific models related to invasive weeds, thinking that might be influencing these values that we saw. In particular, using Landsat data, we created something of a cheatgrass index and a Salsola Russian thistle index, and those are based on the difference between seasonal greening. So we looked at, for the cheatgrass index, we looked at the maximum greenness during the early season, that March-May period, relative to a median greenness during the later season, NDVI in June. So if they're greening up really early in the season, that's suggestive of cheatgrass. And in sort of the opposite would be the Salsola, which tends to green up later. So we're using a composite of NDVI, looking at the average early season and the max later in the season. So they're greening up later, then that suggests it might be Salsola on those sites. And similarly, we use this, the DESI is another sort of cheatgrass index. We calculated one from MODIS, and we have that for every year, so we can associate that with different plug and abandonment dates. We looked at land ownership, elevation, latitude, and then our different drought indices and precipitation. So we're trying to see what influences these have. I'll show you just a couple slides here of how that peatgrass and Salsola indices look and why this is important. So these dark spots here are some of our sites that have already been abandoned that we're studying, and you can see the areas with some still active pads around there. So we calculate those indices, and it looks something like this, where you have these brighter values, in this case, are suggesting Salsola in these areas on these pads. And so this is a single image, brighter areas suggesting non-native vegetation. If we zoom in on some of these, and these are 30-meter pixels, this would be, this is flagged as a Salsola site. If we look at the vegetation from Earth Engines, we can see that this is, we could use more field data for this, of course, but the sort of visual texture of this is suggesting that that might be Russian thistle on those sites. Likewise, we can do this for cheatgrass, and these sort of brighter spots are suggesting early season greening. We could zoom in on some of those, and this is what those pads look like. Here's another example, and this one in particular has a sort of a texture and a signature that suggests that that is cheatgrass, and whatever it is, it's not certainly not similar to the surrounding vegetation. So that's an input to our model. Okay, so the results of what we found in terms of what we call considering revegetation during these 5-year periods for each of these wells, we saw that on average, well, the median was about 25%, the mean about 35%, and we're seeing in general after 3 years and 4 years and 5 years and 6 years that we're seeing an increase in cover at these sites, and this is just aggregated over all these wells. So this is basic statistics. The distribution over our site shows that there isn't a whole lot of obvious visual pattern in these values. So the red ones would be lower RFVC. The higher ones would have higher vegetation cover after 5 years. So no obvious patterns that might be related to sort of biogeography at this scale. If we look at them in terms of when they were plugged and abandoned and how that recovery is progressing over time, we see some interesting patterns that are related to the time periods of abandonment and recovery, which are likely related to the climate in this time period. So these, starting from the red and going into the purple, these were abandoned in 1997. So this group of wells that were all abandoned in 1997, we evaluated them 3 years later in 2000, 2001, 2002, and then up to 2003. And you can see that these sites, this is during a drought period, are kind of plateauing in their recovery. So the drought's having an effect on recovery there. As you get out of the drought period, you start to see more linear revegetation trends in a lot of these sites. And especially in the ones that were plugged and abandoned later in the 2000s, 2003, 2004, 2005, nice or linear trends in revegetation during these periods that had milder climate. And in terms of our random forest model, I want to make it pretty clear right off the bat that this model does not explain a ton of variance in these values, but it's more of a data mining, so we can't really predict what's going to be on the site based on our environmental variables, but we did see some patterns that we thought are pretty interesting. And in particular, we saw from these random forest models that one of the best predictors of high fractional vegetation cover would be that cheatgrass and salsola indices. So a lot of these sites that tend to have the higher values also tend to have likely higher cheatgrass and salsola. We saw some influence of these drought indices in climate. The SPEI, Standardized Precipitation Evapotranspiration Index, came up as important. That typically was important when we looked at that climate or that drought index during the year of evaluation, so 5 years after the fact. Precipitation came in a little bit, some soil variables, and then the other cheatgrass indices. So we're going to kind of just, I'll show you the distribution of some of these variables related to those fractional vegetation values and see some of the patterns. Okay, so this is, again, our drought index, SPEI, and these are our fractional vegetation cover values relative to the year it was plugged. And so if we look at a site here, for example, that we're interested in 1997, a wet year when it was abandoned, and a very droughty year and a drought period during the 5 years of recovery, we can see that those values are indeed pretty low, which we sort of suspect due to this intervening drought period. We have other ones which we'd expect pretty high fractional vegetation cover values because they're wet periods when they're abandoned and relatively normal or wetter conditions when we evaluated them. In these cases, yes, higher fractional vegetation cover values. There are other ones, like these ones in 2002, which, right in the middle of this drought, were abandoned and then evaluated 5 years later with also sort of drought conditions, but the period in between with some wet years. Those tend to have actually pretty high fractional vegetation cover values. Not exactly sure why the 2002 group tended to do so well in those values. That's the question for our further research. Here's a few box plots of what we found. So this is the year of evaluation, so that 5 year after it was abandoned, spring SDEI value. So this is averaged over 3 months in the spring. And we're finding the ones that had the highest RFVC tended to have wetter SPEI during that evaluation year. And that makes a lot of sense, of course. You have a wetter spring, you have more growth and more vegetation response that we're going to pick up with the satellite imagery. If we look at the plugged and abandoned year, spring drought index, not a whole lot of pattern here. We're actually seeing, again, in the higher SPEI values, yes, okay, higher relative fractional vegetation cover, but we're also seeing areas that seem to have higher vegetation cover in these periods that tend to have more drought. So, not sure exactly why that is. There's a lot going on between the time it was plugged and abandoned and the time it was evaluated. It's possible that these ones have higher vegetation cover now because the reclamation efforts that went on during these drought periods just didn't take off, and cheatgrass or salsella took over 5 years later. I'm not sure, that's complete speculation, but there are some patterns to these data. This is our cheatgrass index that we created, and we can see that the ones that have the higher cheatgrass index values also tend to have higher vegetation cover after 5 years. The DESI is also a cheatgrass index, and we see with the DESI, ones that have sort of this moderate, DESI from MODIS, that's 250 meter pixel. We calculated it for every year, so this is more closely aligned to when they were abandoned and when they were evaluated. The ones that tend to have moderate likelihood of cheatgrass also had higher fractional vegetation cover when they were evaluated. And then with the soil variables, those few soil variables came through. I think these might be related to the potential of these sites to actually to have invasives on them. This is soil electrical conductivity, and then the ones with higher conductivity tend to have higher vegetation cover, but nothing too profound here. We found that there were some differences between land ownership, and this is similar to what Travis found in his DART paper looking at 2014 recovery. That the federal and then tribal lands tended to have higher fractional vegetation cover after 5 years than state and private, so some possible differences between land ownership. And then we're seeing differences between the vegetation communities that we've assessed, and so higher fractional vegetation cover after 5 years in grasslands, and then these deciduous woodlands, but that was, I think there's only 10 or 11 pads that fell within this vegetation class. But generally lower recovery on these evergreen woodland and shrub classes. Okay, so what is going on? There's still a lot of questions that we have about what's happening on the ground here. We think that the higher RFVC values that we're seeing on some of these wells is just related to that evaluation year SATV, which is influenced by precipitation and other things that are going on during that year. Also likely related to cheatgrass and Russian thistle on these sites when they're evaluated. And this is another good example of what we see when these pads are abandoned, and there's just this quick jump here in vegetation cover after they've been abandoned, and it usually looks something like this. So it's looks herbaceous. It's green from high-resolution imagery. It's probably not close to perennial vegetation, and that's why we get that rapid response. And so that's a lot of those sites that look like they may have recovered well are actually just non-native grasses in a lot of cases. But the question is, these ones that have these lower values and maybe don't have a lot of invasives on them, what's going on there is they're native shrubs and native grasses that are just happen to be more sparse that haven't fully covered these sites 5 years after the fact. So that's something we want to look into with some more field data down the line. So just to wrap up here, what we found, the time series data that we're using, Landsat, and the analysis approaches seem to be pretty accurate and robust for measuring the dynamics of these well pad sites. We can obviously see when they're drilled and sort of that production phase and how vegetation is changing after it's been abandoned. So they're great for that. SAPI, it tends to be very robust as well, and it's useful for looking at those changes in bare ground over time as the vegetation starts coming back on these sites. Some of the things that we notice is that the spatial data and the satellite imagery and all this are just, it's really noisy, and we're looking at a large area, and so this kind of gets compounded across these analysis steps, which made the modeling, the random forest modeling, not as useful and not as definitive in terms of what's going on. And then there's also a lot of questions about the historical records and GIS data. Are those plug dates really accurate? We don't know. We're just kind of assuming that they are. But as these records progress in the future and we get better at keeping track of this stuff, these time series approaches, I think, are going to be pretty necessary for monitoring and evaluating these sites across really large areas. In terms of what we found in these models, we can say that there does seem to be some year evaluation climate influence. It's pretty apparent that that's affecting what we're seeing, but there's some confounding factors. The later period that we saw the best vegetation fractional cover tended to be a wetter period, but possibly also a period where the treatments are getting better on these sites as well, which is influencing what we're seeing. So trying to sort of disentangle that would help. We found that probably in a lot of these cases where we're seeing high recovery values or fractional vegetation values, a lot of that is likely just mostly weeds. This is definitely not ideal, but I guess on some level it's better than just having exposed ground and soil that's going to fly away immediately. In terms of future applications, we think this is going to be useful to establish operational monitoring of these changes on, particularly on DOI lands and other lands that are interested in these approaches. The technology and data quality are rapidly improving. The satellite data is getting better. The cloud computing is great, so a lot of people can do this from their desktop. Getting more information on the ground is really essential for improving these models. We think these approaches using the time series and BFAST can also be used for other important applications across these regions and drylands. We're looking at OHV and pedestrian trails and military land uses with our DoD partners and how those areas are changing over time. Obvious uses for post-fire vegetation recovery using time series approaches, invasion dynamics of cheatgrass, and then looking at ephemeral waters and other water bodies, how those are changing over time due to drought and climate. So a lot of uses for these approaches that we're pretty excited about. And that's all I've got for you. So thanks, and happy to take questions from anyone.
Great. Thanks, Miguel. It looks like you got some questions. If people have other questions, you can send them to me, the science application. Sorry, I didn't say that earlier. I'm the host, but I don't think the host showed up. They can send them to science applications, and I can read them to Miguel. Miguel, we could start by you answering the questions that you received, and then we can move on to any questions by phone. If folks have questions by phone, you press *6 to unmute yourself and *6 to mute. Also, I know there's some of the co-authors are in the audience, and feel free to chime in via phone if you like to. All right, Miguel, if you go ahead and answer, you can read the questions that you received, and we'll move forward that way.
All right, let me see if I can find them here. Okay. Were all paths included subject to active reclamation? That's a good question. I am going to say no, and we didn't really have that information on hand when we started this. We know some subsets of the data have reclamation information. We can pull those out and probably get a better idea of how those particular sites are responding. I'm guessing some of the earlier ones that were abandoned in 1997 didn't have active reclamation. Most of the later ones probably did. Again, I'm just guessing. We went through each of these sites, these pad sites, and use that Google Earth time slider where you can look at the aerial imagery. And we went through time and noted if we saw obvious signs of reclamation, where patterns in the soil, where the topsoil might have been tilled or whatever. So we did note that, but we just weren't certain. So that's definitely information that I think would help us understand what's going on more. So if anyone has it, please forward it on. And then what types of reclamation that's not information we had at this point. Next question, with such a short time of activity, I wonder if the well was actually functioning and regularly maintained during that time. That's a good question, and we definitely noticed that some of these sites may have been cleared and examined and not used due to whatever reason. And then pretty rapidly after that, they were abandoned. So I'm not exactly sure why, but that would definitely have an effect on what we're seeing as well. And this is just something that we had to deal with based on the time that we have with Landsat. We had to look at these recent years. Others in our group, the SWED group, are looking at longer term revegetation using field data. So they've gone back and developed a chrono sequence of paths going all the way, back much longer, I think 50 years or so, and looking at those. So we should have some sort of different answers once those data are ready. And Mike, if you're on there, if you've got anything to add to that, feel free. I think those are the two questions I can see here, Mary. If there are any more that I'm not seeing.
Okay. I haven't received any. So let's open it up. Does anybody have any questions via phone? So you can press *6 to unmute yourself and ask your question. Also, I'll open it up to any of the co-authors if they have any comments that they'd like to make via phone.
Hey, this is Chris Cole, BLM Remote Sensing Lead. Can you guys hear me?
Yeah, go ahead, Chris.
Okay, great. Sorry, I was on mute. I didn't realize. I have a couple questions for you. So obviously the value of using Landsat is the time series, but it does have fairly poor spatial resolution. Are you guys considering kind of follow-on emergent higher resolution systems like Sentinel-2 on the electro-optical end, or potentially a polarimetric radar?
We are considering, Sentinel would be great, and that's about as far as we've thought through. We have obviously for smaller areas using some worldview and stuff like that. But you know, we were just interested in sort of the longer time series at this point. But I think in the future, definitely high resolution is the way to go for these sites.
Okay, I have another question. So what do you consider acceptable RMSE results for your studies? You mentioned that the errors that you achieved were acceptable. I was just kind of curious what your criteria was for that, if you had a threshold for acceptable RMSEs.
For the remote sensing models or for the random forest?
For the former.
That's a good question. I mean, everything was cross-validated. We didn't actually have a threshold that we would consider successful or not, but I mean, generally, you know, we're looking at our squares over 0.5 it was decent in our book. But yeah, we didn't dig too deep into thresholds for the RMSE. Do you have any input on that you would suggest?
I mean, we could chat further, kind of offline, but I was just curious.
We did look at, you know, the improvement of a single model versus multiple variable models. Of about a 10% increase in that would make it a useful model to integrate multiple variables. But other than that, we would typically stick with a single index or single variable model for most of these things.
Okay, thanks.
Thanks, Chris. Any other questions by phone? Again, just *6 to unmute yourself. I hear some muffling going on, so please mute your phone if you're not interested in speaking. Thanks. Miguel, I don't have any more questions in my queue. Do you?
Not that I see, but you know, anyone, if you have questions, feel free to email me. This is my email up here. I'll get back to you as soon as possible. I'm happy to follow up on a call or anything if anyone wants to talk in more detail about this project. Happy to do so.
Great. Thanks, Miguel. Well, I guess we'll go ahead and wrap it up. It's almost on the hour, or actually just turned on the hour. First of all, I'd like to thank Miguel for presenting today, and I'd also like to thank you guys, our audience, for attending the webinar. For those of you who joined late, I will send you a link to today's webinar recording sometime next week. And I just want to wish everybody a good day, and hopefully we'll see you on November 9th for our next webinar. Take care.